Welcome to week 2 of online lessons. Today we're going to solve simple equations. And what I should have actually wrote is solving simple linear equations. What does that mean? Well, there are equations with letters in them, algebra, something like A. I wrote an X. X or A, or you could even use smiley face, and we'll see why we could use smiley face, but we know that they're linear equations because the actual letters or the variables that we use have a power 1, so they don't have any exponents of 2 or 3 or higher than that. There's actually, well, an exponent of 1. So these are the learning objectives for today. We're going to learn how to solve linear equations, even ones with brackets and fractions. Remember solving these? Box plus 7 equals 12. Yes, you probably remember these from elementary school, and you would have proudly put in the number after maybe a minute of trying to figure it out. You'd put a 5, and you'd be very proud of yourself. In fact, you'd probably be glowing. But did you know you're actually doing algebra? I know. Shh. Don't tell anyone. We were secretly training you all these years for algebra. And some of you would say, wait a minute. No, I wasn't. No, I was not solving algebraic expressions. You were. You were doing it. So what has happened between then and now? Why is it that algebra has this sort of feeling to it of like, oh, no? Well, you probably don't believe me yet, but let's see. Try solving these. Yep. A plus 9 equals 15. You're like, what? A? What? W? 2M? Huh? And this P over 3? Oh gosh, what is that? What are you doing to me, Mr. Lowen? Well, I should say Jamie, Mr. Lowen. It's weird referring to myself as Mr. Lowen. Side note, maybe these look confusing. I know, because there's letters, and letters have this stigma attached to them that they're confusing. Well, they're really not. So, believe it or not, it's the same as solving these. So if I just gave you these boxes, and I said, well, box plus 9 equals 15, you'd say, oh, well, that's 6. Easy. Or this box minus 9 equals negative 4. You'd say, well, okay, that's 5. See, 2 times what number? 2 times a box equals 18. Well, I know that 2 times 9 equals that. And the last one, after a little bit of time, you'd say, okay, negative 18 divided by 3 equals negative 6. But these boxes are no different than what we saw before. These are the exact same equations. 2m really is 2 times m. Remember, when we're doing multiplication, a 2 attached to a letter is just a multiply. This is the same as 2 times some box named m. So, spoiler alert, if I were to actually name these boxes A and W and M and P, well, we actually just have the same thing as before. Mind blown. I know. So you can actually think of these letters, so when you see algebraic expressions, you can think of them as placeholders, or really just kind of boxes. And letters don't always represent just a placeholder. Sometimes letters like pi, for example, represent something, legitimate, 3.14, blah, blah, blah. Or sometimes in physics, we use the letter E to represent some constant value. But in this case, when we're talking algebra, we actually just use letters as placeholders or boxes. So you can actually think of letters as placeholders. And remember from the last lesson, we actually call these letters variables. That's the official name for them. But this is why you should not fear algebra. It's really the same thing that you did before. But sometimes things get a little more difficult, and we need to learn what sort of tools we can use to solve these algebraic expressions, especially when they become harder. But you're still asking me, well, why couldn't we keep the boxes? They were so much, times were simpler way back when. Well, look at this one. So try solving this equation here. Yeah. No, go ahead. Well, some of you may be thinking, well, okay, that's a little more difficult. And I would say, well, are these supposed to be the same number? Or can they be different numbers? Because if they're different, then I can probably do it a lot easier than if it's the same one. Well, that's exactly why we have to use letters, because we don't know whether these boxes are supposed to be the same or different. So if I were to actually label these things y, then I would know that, oh, I'm solving for some value y, some letter, some box, but these would both be the same. So this is why we couldn't actually keep the boxes. Most equations are more complicated than the ones that we just saw on the last slides. Also, when there's more than one variable, we can't necessarily use boxes because boxes look the same. And last one, mathematicians are lazy and letters are easier to write. So there. So let's go on. What's an equation? Here's the official definition of an equation. An equation is actually a statement that two mathematical expressions are equal. We saw this in the last lesson, and we saw that we'd have things like, let's say, 7ab minus 5 plus 2ab minus b squared. So this was actually an algebraic expression, and we knew that this one has 4 terms because each term is separated by a plus or a minus. But this is an algebraic expression, and an equation is simply taking 2 of these and setting them equal to each other. So we're just going to talk about linear equations. So these variables that we use only have a power of 1 on them. And here's a couple examples of an equation. X plus 7 equals 12. Or this one here, 7p equals 16 minus p. So this letter, I'm going to come back to the letter here. Sometimes the letter seems, students have trouble because they think the letter should have some sort of like meaning. But I'll tell you the truth, as far as algebra is concerned, I could have actually just wrote this other one as c plus 7 equals 12. Either case, we're solving for x or c. It really doesn't matter, because remember, that letter, we can think of it as a placeholder. It could have just been a box, but we're using letters instead. This other one could have been 7q equals 16 minus q. It really doesn't matter what letter we're particularly using. So the value of x or p that makes these equations true is called the solution, or the root of the equation. Root is a less common term used, but it is one that we'll use in this course. So to solve an equation actually means to find the value of that variable that makes the equation true. To solve this one would mean to find the value of x, or the box, that makes this thing true. And same as this one. It would be finding the p that makes this thing true. So what about when we're solving these equations? So the first thing that we actually want to do is we want to isolate the variable, which really just means we want to get that variable by itself. The variable is the letter. We've got to get it by itself. And how we do that is we perform the same operations to both sides of the equation. We call this the balance method. So more officially, the balance method could be written as like a commandment. Thou shalt do unto one side as thou hast done unto the other. This is just a way of saying if you're going to do something to one side of the equation, you have to do it to the other. You could think of it as a balance or an actual scale, where we've got the equation written out and the equal sign represents the fulcrum or the balance point. So if we're saying that 2x plus 3 equals 9, what we're really saying is that if we're going to be messing with this side, for example, like subtracting 3, we have to start subtracting 3. We have to subtract 3 from the other side too. Otherwise, this equation will be unbalanced. So we need to keep it balanced by making sure that if we ever perform any operation on any side, we do the exact same thing to the other side. So let's see what this means practically. Here's the same example. And what I'm going to do is I've got to get x all by itself. And in order to do so, I got to get rid of 3. So I kind of gave it away on the last slide. But I'd like to get rid of that plus 3 so I can subtract 3. But if I do it to the left side, I have to do it to the right-hand side as well, because this has to stay balanced. So my next line would be 2x equals, and 9 minus 3 is 6. So technically, I haven't changed anything here. I've just taken away something from both sides, but it is still true that 2x equals 6. Now, the last thing I have to do is divide both sides by 2, because I want to get rid of that 2 attached to the x, and we're left with x equals 3. Now, I went through this one fairly quickly, but that's because I have a pictorial diagram using tiles to model some other equation. So if I wanted to model this equation here, 2x plus 2 equals 6. Remember, equals is sort of the middle of the scale. So we've got 6 things, 6 singles on this side. You can think of them as 6 tiles. I've got 2 tiles on this side. That would be that 2, the plus 2, and 2 x's as well. So these are just sort of some length long, but we've got 2 x's and 2 singles equals 6 singles. That's really what's going on here. So using the balance method, if we want to actually kind of get one of these x's by itself, that's really the goal here. We want to get x all by itself. So the first thing we could do is imagine taking 2 tiles from each side. So I'll scribble them out. But we know from using scales that if we took 2 off from both sides, this scale would actually still be balanced. And so would our equation. So this is exactly why it's important. And as far as the equation goes, it's like subtracting 2 from the left and right hand side. And what's left is 2x plus 4. Okay? We still need to get x by itself. We've got 2 x's on the left side and 4 singles on the right hand side. So what we can do is we can actually split both of these in half and remove half of them. So if we move half of what's on the left-hand side and half of what's on the right-hand side, we're still keeping this scale in balance. That would be like dividing by 2 on both sides of the equation. So what we're left with is x equals 2. And we can see it pictorially here. We've got an x all by itself and 2 singles left. But every step of the way, we were doing the exact same operation to both sides of the equation. So let's see some actual examples without the scale.